So far we have discussed what is meant by a sampling distribution of estimators, and we have derived what is called OLS estimators for fitting a line to a sample of paired values x and y. And we are going to now investigate the properties of this OLS estimators of, say, intercept term and the slope term that we had derived. But before that, to fix the idea and to realize what kind of things really happen, let's learn this, or rather relearn this again with a numerical example. So this is the data that we have got. This is the data on x and y, and as it happens in OLS, we are going to believe that it is the x which is primarily a determinant of y. It linearly determines y, meaning thereby the relationship between y and x is like a plus bx. Of course, it could be minus as well in estimate. But we know that the one value that we actually observe contains something more, which is the random term, and we have no really clue about what that random effect is. So what we effectively do is, we look at the data, plot x and y as values, fit a line to that such that the error term affects y, and therefore it forces y to depart from the line fitted. And that's how we are going to discover a line such that the departure of y from that fitted line, when taken as a square and sum, should be minimum, and that's what we mean by having the ordinary least square estimators. And we know that these estimators that we have derived are of the type where we get, in fact, there are two ways in which we usually write it. Firstly, let's call it as what are called OLS normal equation, and they are of the nature yi equal to n times a plus b times summation xi, and summation xi yi equals a times summation xi plus b times summation xi square. These are the two simultaneous linear equations which we derive. They are the result of the condition that we impose, that if the relationship between y and x is of this type, you can write that, probably I have written u, I will stick to that. Then the summation ei or summation ui, the random term, in squared form added up, should be minimum. So if we want to choose that the square of the random term summed up is to be minimum, what kind of an a should exist and what kind of an b should exist? Therefore, we solved it with using the elementary results of the derivative, that the first derivative should be set equal to 0 when we minimize something, and we get this condition with respect to a, this condition with respect to differentiation of summation ui square with respect to b. If written in the matrix form, it looks like this: summation yi, summation xi yi equal n summation xi, summation xi, summation xi square multiplied by a and b. Effectively solving therefore for the unknown vector of a and b, we will be required to multiply both sides by the inverse of this metric. That's the way in which it will be represented in matrix form. In fact, it is also equally important to realize an alternative way of looking at these very same equations in a slightly different manner, which we will do subsequently. But this is one kind of a representation that you can often come across of these very equations, which is metric representation. And if we solve these as two simultaneous equations, with a and b being unknown and all other quantities derived from the known data, the solutions that we get for a is equal to y bar minus b times x bar, and for b we get the solution summation xi yi minus n times x bar square, whole thing divided by summation xi square minus n times x bar square. So summation xi yi minus n times x bar y bar divided by this. This in alternative rotation, if we have the data not in the original form but instead in form of deviations from the respective mean, it would appear as summation small xi yi. This is also a notation which is used in many textbooks, and this would be same as summation small xi square. That means square of deviations of x from its own mean summed up. This is also represented in form of uncorrected sum of squares like s of xy, and not uncorrected in the sense not corrected for degrees of freedom and s of x. They are just the alternative notation which appear in different textbooks. When in matrix form, it will be same as, this will be considered as the vector. The solution for that would be equal to inverse of this matrix multiplied by summation y, summation x, y. And this is an inverse. This is usually called as the x transpose x, and this is x transpose x inverse multiplied by x transpose y, and that's how the solution for this vector is written as x transpose x inverse into x transpose y. We have derived this in the matrix form earlier. They are actually the same thing. All that differs is either a notation or the form of representation. Like in this case, it's just a matrix representation of the very same simultaneous equation that we solve for. Now it is these formulas, whichever that suits you, whichever that fits more easily, which is more convenient to compute with, you can use. And now we apply these formulas to the numerical examples. What do we get? We get for this data, what are the statistics that are needed? As it is obvious, all that we need is a data like this. We require n number of observations, summation xi, summation xi square, summation yi, summation xi yi, and that's what we have got these data here. So this is a numerical example of with relatively easy numbers to operate with. If you look at them pairwise, just think what guess can be made. Suppose if I take y by x, this is roughly, y is roughly twice the x. Here it is little about twice the x. Again, here again it is about twice the x. Here it is twice the x but one less. It would have been 10. And again here it would be 18, but it is 17. So there is something which is making, otherwise even from this data one can guess that value of change in y to change in x would be somewhere around 2, because individual values look like as a ratio closer to 2. So let us see what actually turns out. So what are the quantities that we need? We need xi, yi, because where do we need them? We need them in calculating from this formula. We also need summation xi square, we also need summation entire x bar square. All these quantities are there, which can be more readily computed. Sum of x values is 20. There are 5 x values, so 20 divided by 5, so the x bar must be equal to 4. Similarly, y bar must be equal to 8. This is a quantity which is what we call covariation quantity. We are taking product of x and y and summing them up, that is to 30. And if we were to calculate something that we defined as s of xy, or alternative equal to summation xi yi, what is the formula? The formula is we take summation xi yi, that is product of xi y values, subtract from them product of mean multiplied by n. So again, we can plug in this quantity. We already have knowledge of n and x bar and y bar. If we plug in there, what we get is in fact the covariation. So just take what we would get. We can easily get this as sum of xi y is to 30. Subtract from that n, which is equal to 5, x bar, which is equal to 4, y bar, which is equal to 8. And therefore, if we take the multiple of this is 32 multiplied by 5, And 32 multiplied by 5 would give us what? It would give us 160. So what remains is 70. So our f of xy, or this numerator that we are going to use, is going to be 70. Now similarly, we would be required to compute the variation of x, or there is s of xx, alternatively summation small xi square, and that would be equal to this, which is summation xi square minus n times x bar square. Again, plugging in the values from here, we get summation xi square equal to 120, n equal to 5, and x bar is equal to 4, therefore 4 square would be equal to 16. So it is going to be 5 into 16, that means 120 minus 80, that is 40. So our estimate of this quantity that we need in the formula is going to be equal to 40. So our estimate of B is going to be 70 divided by 40, which is in fact in decimal format 1.75, pretty close to 2. The initial case that we made. It's not necessary that you should make this kind of a case, but sometimes data automatically suggests that, and that's also one way of checking and making sense of data. Having got the value of B, we know that by using the relation that A is equal to y bar minus B times x bar. Now we have got a y bar, we have got x bar, and we have got the estimated value of B. That is going to give us the value of A, y bar being equal to 8 minus B is 1.75, that is our estimated value of slope, multiplied by 4. So, what is the estimate of A? This is the estimate of A, which is equal to the value that we get 1. We can also transform this whole data in form of deviation forms, which we are going to use. This is 4 times 1 point, that means it's closer to 8, only 0.25 less for the 1, and then this will equal to 1. This will be equal to 7. So our estimated equation is going to be y hat equal 1 plus 1.75x. So this is our estimated equation. What does it mean? It means now we can generate something what we have defined as the estimated value of y, which means we plug in these values of x and then we will get an estimate of y. What will be these values? These values are going to be listed in this column. We can compare this with the actual y. The actual y is 4, our estimated y is 4.5. 7, 6.25. It is 3 here, it is 2.75. It is 9 here, 9.75. 17 here, 16.75. Take the sum, and again you will notice that we are derived. The values estimated are going to be in close connection with values actually observed. In what sense? The summation yi of actually observed values is going to be equal to summation yi hat. This is y hat. So if I add up all y hat values estimated from this equation is 40, which means in total there is no really departure now anymore in y values. They agree in their total. So now let us look at what could be the error values. What do you mean by error values? Look at the actual y, subtract from that the estimated y, which is generated by these equations. So what is the difference? The difference is 4 minus 4.5, that is minus 0.5. 7 minus 6.25, that is 0.75. 3 minus 2.75, 0.25, and so on. So these are the error terms. They are the difference between the actually observed y vis-a-vis estimated value of y generated by fitted straight line. And now again, if you sum up all these error terms, what do we get? We get some of these error terms in fact add up to 0. In fact, that's what we have predicted. that the error terms will add up to 0. Why? Because we are trying to minimize error terms. So the best way to minimize is in fact to generate such values of EI, or rather to have a formula which will give such values of EI which add up to 0. Evidently, if some of these add up to 0, the mean of the error term will also be 0. This is something which is inbuilt in OLS equation. In this sense, we don't have to assume that the error term must have a mean 0. OLS equations have this as an inbuilt condition that the error term generated by OLS are going to add up to 0. In this sense, our sample estimate of the mean is going to be equal to 0. But any mean for that matter is not useful unless we relate it to some quantity of dispersion. Therefore, what we do is, just as we do it in case of other variables, we try to compute what can be called as variance. And what do we mean by variance? Take the original value, subtract from that the mean of that variable and square. In this case, the mean turns out to be 0, so all that we need to do is EI minus 0 square. 0.75 minus 0 square. So we don't have to really bother. We have to, whatever estimated error terms that we have got by the fitted equation will be simply squared. When we square them and add them up, it is 1.5. What is this 1.5? Summation EI square, as we have derived in fact this earlier algebraically. We know that this 1.5 is in fact the variability of y. What is the variability of y? Can we talk about variability of y? We can, because we have got summation yi square and we have got the mean of y. And what is the variability of y? The variability of y will be given as just we did in the case of x. We can compute variation or sum of squares of variations of y, that is summation yi square. Alternatively, the equation of the notation of the type that we have used as derivations of y, or alternatively we can also take this as summation yi square minus 3 times y bar square. So if we do this, what is it that we will get? We will get summation yi square. This is summation yi square, 444, minus L, that is 5, and this is going to be 8 square. So it is going to be so our estimate of S of y, alternatively equal to summation small y square is 124. And as we had seen, the overall variability of y comes from two sources. What are the two sources? The linear relationship of y with respect to x and the influence of the random term. What is the overall variability? Now our answer for the overall variability is 124. But now there are all the square terms. So our overall squared variation of y from its own mean is equal to 124. How much is a part of that which can be attributed to this disturbance term? The answer here is sum total of squares of error terms, which is 1.5. Which means, in our notation, what can be called as the residual sum of square, we are going to take S of y, that is 124, and subtract from that 1.5. The remaining part is something that is really attributed to relationship with y. And as we had derived, you can write it equivalently. Relationship with y is r square into S of y. Relationship with x will be therefore 122.5, and 1 minus r square into S of y is going to be 1.5. So it is this part which we have actually estimated. Of course, we don't have to do this individually, but once you do it with these simple numerical values, it becomes easier to understand what is going on, because nowadays you can simply plug in this data in a spreadsheet like software which readily computes you most of the statistics needed. But In this case, now if you try to relate what is R, what is R square? Again, from the raw data, we can calculate R square. We have got summation xi yi. We have got s of yy. We have got s of xx. So we can calculate the R. So I leave it to you to find out what that R would be and take the square of that R, multiply it to 124 and you will get this answer. So the R square would be fairly close, something like 0.98, which means, in very crude rough terms, it means out of the total variability of y, with its relationship with x, the total variability of y as related to x is out of 100, nearly 98%. Whereas the remaining small portion is in fact due to the contribution coming from the random shock term. So this is something which can be again reworked. Instead of doing in original values, let's also do it in deviation form.